Hello students, welcome to lecture 35 of the online course Introduction to Microwave and Optical Metamaterials. Today's lecture will be continuing our discussion on metamaterial-inspired antennas. So, we will be covering these two topics mainly. We will discuss about gain enhancement using metamaterials and how we can obtain isolation using metamaterials. So, let us first look into gain enhancement of antennas using metamaterials. So, as we all know that gain is one of the most important antenna characteristics, especially in fixed point to point communication and radar systems. What are the benefits of high gain? So, antennas with high gain are able to increase the communication range for a given transmitted power, and they are more resistant to interference. So, question comes, how high gain is achieved? So, the first thing is that directivity of an antenna is proportional to its aperture size, and thus it becomes obvious that deployment of electrically large antenna will give you higher gains, right. So, typically it is a common practice to use electrically large antennas or arrays with many radiating elements for achieving higher gain. Now, all is not good here, because you cannot now keep on increasing the electrical size of the antenna, because you basically have size constraint when you go for any practical application. So, that way the relation between antenna directivity and size basically prohibits the usage of small antennas for several applications where high gain is basically required. So, it becomes obvious that you want ultra compact yet high gain antenna platform, but then these are difficult to implement. So, what is the proposed solution? So, you can use metamaterial radomes or superstrates or lenses as low cost gain enhancer. So, that can allow you to improve the antenna gain. So, they will have the form factor advantage, okay. So, you can basically increase the gain without significantly increasing the antenna's volume or footprint. You need to place the structure above the radiating element, so the placement becomes crucial, and the operating principle remains that it basically modifies the far field radiation pattern by interacting with the electromagnetic fields in the vicinity of the radiator. So, main metamaterial based techniques which are capable of accomplishing this kind of gain enhancement are basically this. First is the placement of ZIM, that is zero index material, or NZRI, that is near zero refractive index material, as superstrate. Then the second method will be deployment of AMC, that is artificial magnetic conductor surfaces in the vicinity of the radiators, and third will be the placement of green, that is graded refractive index metamaterial lenses in front of the camera. So, we will basically look into each of this category in little details to understand how they work. So, first let us consider zero index material or near zero refractive index material as superstrate. So, near zero refractive index material has got refractive index which is close to 0, that is obvious from the name itself, right. Now, given a metamaterial slab which has got a refractive index close to 0, according to Snell's law, you understand that the transmitted wave in this case will be focused perpendicularly to the medium interface regardless of the incident angle, right. So, something like this. So, you have any incident angle, but if you have a material that has got a 0 refractive index, the transmitted wave will come out in normal to this particular interface. So, particularly Anok and his group demonstrated that the radiation beam of an antenna which is embedded in a metamaterial will be refracted in a direction that is very close to normal when the refractive index of the metamaterial medium is very close to 0. That is what has been shown here. Now, this interesting feature of transforming spherical waves into planar waves can be translated into a gain enhancement when such a medium is basically used as a superstrate, or it can be used as an enclosure for an antenna. So, some examples are here. So, you can think of a superstrate which is consisting of this kind of metallic square rings whose two corners are basically connected with a metallic diagonal strip. So, this design was proposed by Panda and his group. Okay. So, as I mentioned, all these different designs are described in this review article that you see in the reference. You can go to this review article to read about more. There you will get the reference of all these papers, individual papers, and you can go into the details of individual design and see how they have made it. So, I will just give you a brief overview that what they have done. So, this is basically the near zero refractive index metasurface, and this is how the side view of the antenna. So, you see this is the patch antenna, okay. You have this PEC ground, and on top of that you use this metasurface as a substrate. So, what is the speciality of this? The metallic square rings basically exhibit zero permittivity at 2.6 gigahertz, and this near zero refractive index substrate, when it is placed at a distance say lambda by 12 above these two microstrip patch antennas which are also operating in the same frequency, then you will get some gain enhancement. So, this structure was fabricated and the gain of the patches basically increased by 3.4 dB, while the low profile of the antenna array was maintained, right. So, a similar kind of unit cell design was again tried by another group, Augustine and his group, and they have done the simulations where they actually changed the design little bit. In this particular superstrate, instead of having this kind of solid rings, they basically took this kind of small gaps in the rings, and this is the patch substrate in the ground. Okay, they simulated this and they found 6.2 dB gain enhancement because of this superstrate, okay, which is a near zero refractive index material. In parallel, other groups also developed some other designs, like Meng and his group. They proposed a combination of MSRR, that is modified split ring resonators, and small patches as metamaterial cell that you can see in this figure. Okay. So, these are basically the split ring or modified split ring resonators, and then you have this metallic patch on the right. Okay. So, there the advantage of a superstrate synthesized by this kind of cell they have seen, and it has found that it is easy to tune and match to the characteristic impedance of the free space. So, they have done the experiment by putting a H plane horn antenna and a patch antenna like this. Okay, this is the patch antenna, the side view. This is where they have put this superstrate. Okay, and they have seen that when you integrate this zero index superstrate for this horn antenna and the patch antenna, you can get almost around 4.43 dB and 6.6 dB gain enhancement respectively, right. Now, the same concept was again modified, and in similar pattern of experiment was again done by Suthar and his group. So, here they have made a metamaterial lens which is basically nothing but an array of S shaped, you can see here S shaped metallic strips which were designed and fabricated. So, the placement of this single lens over a WLAN patch antenna. So, this was a WLAN patch antenna. They have placed at a height h. Okay, you can see in more details in this paper about all these parameters and the design specifications. So, this gave 0.6 dB enhancement, okay, when they used double lens. Okay. So, this is another structure where you have FR4 separator, and then you have 3 layers of ELC, that is electric field coupled resonators. Okay. So, these resonators were utilized as a radome for the patch antenna. So, this is where the patch antenna is lying, okay, and this is the unit cell of the design, okay, or the resonator. So, this was done by Lee and his group, and they realized that the gain was 80% of the radiation of a perfect radiating surface with the same area. Okay. So, the 3 layers of resonators were separated by FR4. Okay. So, this proposed structure accomplished a remarkable 7.8 dB gain enhancement as compared to the conventional patch antennas, right. Now, there is another design which was proposed by Kauthar and his group. So, they designed and analyzed a rectangular microstrip patch antenna, okay, that is operating. So, that is the patch antenna. Okay. So, it was operating in the microwave band and they choose the frequency of 5.8 gigahertz, and then they used a metamaterial of layer, like it's basically a complementary split ring resonator, as you can see, circular ones. So, this is a circular complementary split ring resonator, and the metamaterial layer was based on 9 by 9 matrix of such arrays. So, this is basically the front view, this is the side view of this. Okay. So, you can see how it is placed similarly at a height h. Okay. So, this basically allows the beam focusing of the microstrip antenna to be enhanced by around 4 dB, while the bandwidth was improved due to the presence of this meta surface. So, what it tells that all these different kind of designs people have tried to come up with this non-zero refractive index materials. So, they allow you to improve the gain of the antenna without basically increasing the footprint. Okay. Next, we will look into the deployment of artificial magnetic conductor surfaces near the radiators that can also be used for gain enhancement. So, artificial magnetic conductor surfaces, they basically have great potential for gain enhancement, and a standard configuration of this can be seen here. Okay. So, you have this elements. Okay. So, this is basically your AMC, and you have the radiating current going this way. So, people have made, so this is the design shown by Prakash and his group. So, here a dual band AMC was designed that consisted of a square patch with annular slots like this. Okay. So, this structure was placed at a distance lambda by 8 behind a wideband patch monopole, and this resulted in a gain enhancement of almost 10 dB. Okay. While it also performed better than typical PEC reflectors of the same size. So, artificial magnetic conductors are very good in enhancing the gain. So, there is another design proposed by Esimonis and his group. They basically optimized an electromagnetic band gap structure in order to maximize the frequency window in which the wave propagation is basically prohibited. That means, the waves have got imaginary wave number, while such a structure exhibited a reflection phase response. Okay. So, a dipole antenna was basically proposed in terms of reflection coefficient. Okay. So, a dipole antenna was improved in terms of the reflection coefficient and the gain when it was placed at a distance of 1.5 mm from the top of the EBG surface. So, here you can see this is the unit cell of the EBG, electronic band gap structure, electromagnetic band gap structure. Okay. And here you have the two coupled patch antennas which are separated by this overall structure. This is basically a 3 by 4 periodic cross EBG structure. Okay. So, what is the advantage here? The proposed structures are easy to fabricate, which are solely based on metallic surfaces on layer interfaces, as you can see, and because of this structure you can obtain a gain enhancement of 5.7 dB, while the operating bandwidth, while contrary to PC placed within the operating bandwidth, this is in contrary with the PEC when placed at the same distance from the antenna. So, when you compare a PEC placed on the antenna and then you have this electromagnetic band gap structure placed at the same height from the antenna, you see a 5.7 dB gain enhancement in the later case. Next, we will discuss about placement of green lenses in front of the antenna. So, green are basically gradient refractive index lenses. They are known for their ability to focus electromagnetic radiation, and they can be useful for transforming spherical waves to planar ones. So, this can be accomplished by a gradual variation of the refractive index. So, you can have refractive index as a function of both x, y and z, all three. So, x, y, z are basically the Cartesian coordinates, and this allows you manipulating and shaping of radiation beams. So, a green lens can be synthesized by different layers, which are basically metamaterial layers or meta layers, where each one of them will consist metamaterial cell that basically exhibit different index of refraction, which is coming from their different geometry. So, you can think of this kind of a distribution of the refractive index along the cross section of a spherical Lundberg lens that you can achieve by placing different type of metamaterials, okay, along these different positions. Okay. So, what are the advantages of this kind of green lenses in comparison to the previous method? The first one is that they have wide bandwidth and low loss, since the metamaterial cells are far from their narrowband resonance, and that basically can offer great performance. So, Singha and his group, they basically reported a lens which is composed of thin wires, where 7 layers were basically placed in front of a wideband monopole at a distance of lambda by 2 at the center frequency. So, the gap between the antennas are 4 mm, like the thin layers, which are basically, you know, these are the lenses which are composed of thin wires that you can see, right, all are going through. So, this is basically the fabricated structure. You can see they have put foam in between the green lenses. Okay. So, you can see the thin wires all are having different sizes. Okay. So, this is an antenna, the same thing done in experiment. Okay. So, because of this green lens, the peak gain of this basic monopole antenna was increased by 5.3 dB at 8.8 gigahertz, which was the center frequency, right. So, another interesting feature will be the placement of green lens, right. So, it is important to note that these green lenses can enhance the radiation towards a desired direction regardless of the incident waves incident angle, okay, or you can say input waves incident angle. So, this basic characteristic emerges in symmetric lenses, and therefore, it is attractive for beam steering application, where the gain has to be high as the steering angle varies, and not only towards the bore side direction. So, this can be seen in this figure, where the spherical waves of the feed antenna, okay, are transformed to planar waves at the output of the green lens, okay, and that is independent of their feed's orientation, right. So, this is coming straight and this is coming at a oblique incidence, but you are getting plane waves at the other side of the green lens. So, although the lens here is shown as just a square or a rectangle for simplicity, but typically it has a symmetric shape. So, what are the important takeaways here is that, you know, when you use NZRI, that is near zero refractive index metamaterial as superstrate, they are best suitable for antennas that already have a directive radiation pattern. You can think of using AMC surfaces, okay, artificial magnetic conductor surfaces, which are good for turning omnidirectional radiators into directional ones, and then you can think of green lenses where they show superior performance in terms of bandwidth. They are compatible with beam steering or beam steerable antennas, and they can keep the gain nearly constant over steering using symmetric lenses. Moreover, they exhibit lower loss, but they are more complex to design in comparison to the above two materials, that is NZRI and AMC surfaces, as multi-layer gradients will be required. So, this is the summary or the takeaway from the gain enhancement of antennas using metamaterials. Now let us look into the another aspect, which is isolation, how you can achieve isolation using metamaterials. Now isolation is of great importance for different applications in which antenna elements are basically placed in close proximity due to either the system design, that is typical lambda by 2 inter element spacing needed in an antenna array combination, or for minimizing the overall structure volume. So as a result, crosstalk may rise, okay, due to the basic electromagnetic coupling between the antennas, and in particular for planar antennas that are basically printed on the same board, surface waves are regarded as the main source of crosstalk. Now these surface waves are basically TE or TM modes that can propagate along the antenna substrate and get diffracted on the air dielectric interface. Now you can see the cutoff frequency of this Fc will be, or NC, I think this is a subscript, divided by 4h square root of epsilon r minus 1. So Fc is the cutoff frequency, N is 1, 3 dot 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 for TE, and N will be 0 to the even numbers for TM. H is basically the substrate's height and epsilon r is the relative permittivity of the substrate. So how you obtain isolation using metamaterial? So you can see here that this is basically a coupling due to surface waves in a multi antenna platform. So this is different antenna elements that you see here, this is the dielectric and this is the ground plane, and this is how surface waves are propagating. So it is clear that when you have TM0, that is getting always excited, and it is not possible to prohibit its propagation with proper substrate design. Furthermore, in the applications such as repeaters, beamforming, MIMO, radars, etc., that will require decoupling of antennas and suppression of surface waves for optimum performance. So the emphasis therefore is placed on the isolation enhancement in planar antenna technologies, since they are low profile and they are basically suitable for most of the applications, but they have the limitations, and because they suffer from high coupling due to excitation of the surface waves and space waves. So more specifically, if you consider a compact MIMO platform consisting of two printed monopoles, okay, like this, okay, which are operating at 2.4 gigahertz, you can see this coupling happening. So that was examined by Kedzaki and his group. So they considered the distance between the two antennas to be lambda by 8, and thus the coupling between them, that is S21 and S12 coefficients, has a very high value of minus 5 dB. So what they have done, these authors basically proposed an easy way to fabricate an effective solution. So they first basically examined the electric field of the structure, and in order to find the path through which the power flows from one antenna to another. So after observing the electric field pattern and the way the electric field gets coupled to the other one, they placed a capacitively loaded split rectangular loop that is called CLSRL, okay, that they put exactly at the point where the power flow is maximum. So when they do this, that power is basically getting coupled here. So you are basically allowing the two monopoles to get decoupled, okay. So in this manner they could achieve 30 dB coupling reduction, okay. So further enhancement in the design happened, where people put two meander like structures placed between two closely spaced patch antennas, and that also gave decoupling between the two antennas, whereas they are very close physically located, okay. So in this case, this resonator could provide an isolation improvement of 16 dB at 4.5 gigahertz. Mu negative isolation technique can also be used for densely packed monopoles, as you can see here, okay. That was proposed by Thumularu and his group. So, this group considered this metamaterial structure as a filter that basically decouples the antenna over the whole operational bandwidth. In a similar manner, split ring resonator inclusion pairs were inserted between monopole antennas, okay, as you can see here, that was proposed by Dept and Swillam, and they could obtain 25 dB coupling reduction, okay, while the impedance matching of the antennas were not affected. So, these are the two antennas which were monopole antennas separated by lambda by 8, and there they put this SRR inclusion which has got a plastic support in between, and they gave this much of 25 dB coupling reduction. Liu and his group, they presented a systematic approach for a dual band metasurface design that significantly could decrease the coupling between two adjacent element into frequency bands. They consider 2.6 and 3.5 gigahertz. Okay. So, this is how you can see the unit cell is. So, this metasurface basically consists of double layer cut wire which are of different length, and they are basically placed above the antenna as a superstrate. So, these are the feeds of the antenna, and this is the metasurface. So, this is basically a two dual band antenna. So, you can see that the dual bands, these are the bands, and because of this structure, this is another structure that is proposed by Panda and his group. So, here these are the antennas, and there in between they basically designed electrically small CSRR based antennas, okay, and they placed them very closely. So, you can see 2 by 3 CSRR slots being placed between the two antennas, and the edge to edge spacing between the antennas were only 10 mm, okay. And because of this distance, when they put this kind of a 2 by 3 array of this modified split ring resonators or complementary split ring resonators, that could exhibit a band gap in the corresponding frequencies, and they allowed reduction in the coupling in both the bands, okay, in both of these bands. Finally, you can also think of metamaterial isolators like single negative or double negative materials. They can give smart low profile decoupling with minimal impact on the antenna size or the behavior. However, the main limitation can be attributed to the nanoband metamaterial response, which will be challenging to decouple wideband antennas. However, in parallel, most of the work regarding this isolation have focused on antennas for communication system, where the specification is less strict. So, typically like -20 dB for MIMO arrays. Radars on the other hand are more demanding, and they require as high transmitter receiver isolation as possible. So, you can basically think of this kind of metamaterial solutions to provide extreme levels of isolation, okay, even below -100 dB, where it is necessary to improve the radar performance while maintaining a low profile by avoiding placing large metal sheets between antenna and receiver. So, that is where metamaterial can play a big role. So, with that we conclude this lecture. So, next we will be discussing negative index metamaterials. If you have any query regarding this lecture, drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.